We're going to spend some time looking at the topics following Chapter 2. And the reason is, I think it's important to see some of the applications of the theory so it doesn't just become so much twiddling with symbols. The first topic is a theoretical topic, fields. Now, I'm not actually going to cover this, but I would like to point out that a field is a mathematical structure. And in vector spaces that we've looked at, the constants that we've looked at have all been real. And all the vector space axioms have involved real constants. So our vector spaces, all the constants have been real. Now, in general, you can have more general vector spaces, and in more general vector spaces, the constants don't have to be real. They could be complex, or they could be drawn from some other mathematical structure. But this other, whatever mathematical structure you choose, these constants must be from a field. Okay, and field satisfies these axioms. They're generalizations of properties that are satisfied by real numbers. It's interesting that there are some finite fields. Of course, the real number is an infinite field, but there are some finite fields. And these are very important in applications, in particular in coding theory. And I'm not going to say anything more about this. So I just thought you should be exposed to that concept. The next topic is crystals. And you know crystals are a regular array of atoms. And the point in this section is to relate the crystal structure to a basis of vectors. And I think I'm just going to let you read that. Here you can certainly see indications that we have a basis of vectors here. You take one vector this way and one vector this way. And any lattice point here is going to be an integer linear combination of those basis vectors. Here the situation is a little more complicated. He actually defines this basis. Now, of course, not every lattice point, not every linear combination of these two vectors is a lattice point. There are rotations involved also. But I'm not going to get into those details. I did assign a couple of exercises from this section. I would like to spend a little more time talking about voting paradoxes to help you get through this chapter. Very interesting and also a subject of current research. So imagine that you hold an election and you ask people to rank their preference of three candidates, Democrat, Republican, and third party. So you can see there are 6 possible rankings. How do you get that? Well, there's 3 possibilities for the most preferred. Then for each one of those, there's going to be 2 possibilities for the next most preferred. And then after that, there's only 1 possibility left. So that's how you get 6. Or you can simply enumerate all of the 6 possibilities. Now, certainly these numbers are possible. Each individual has a vote, and each individual may have a different preference. Now, the interesting thing about that result is that if you tally these up, we can get the total preference of each candidate over each other candidate. For instance, consider Democrats and third party. So here we say, if we say Democrat is better than third party, or third party is better than Democrat, here we have 5 people saying Democrat's better than third party. Here we have 4 people saying Democrat is better than third party. Here we have 2 people saying Democrat is better than third party. Here, because third party is ahead of Democrat, we have Democrat is less than third party, so we have 8 on this side. Here we have Third party had a Democrat for 8 voters here. And here we have third party had a Democrat for 2 voters here. Okay, we add these up. On this side we get 11, and on this side we get 7. Did I do this wrong? You get 18. Okay, so the net preference is 7 third party over Democrat. That's where this 7 voters comes from here. Now, if you tally up all of the other preferences in the same way, I won't go through that, but you should be able to do that. You find that third party is preferred over Democrat, Republicans preferred over third party, and Democrats preferred over Republican. That seems kind of strange. There's no clear preference among the 3 candidates. Okay. All right, so what are the implications here? Okay. For instance, here it says that when you have a case like this, it's possible to manipulate the vote. Let me get this out of here. For instance, suppose that you first ask for an election between Democrat and third, and then ask for the winner to run against Republican. Well, if you had Democrat and third going first, then the third would win over the Democrat, and then the Republican would win over the third. So you could make any candidate win depending on the order of elections. You can see also that there's a similar issue if you have a tennis tournament. The outcome of the tennis tournament is going to depend on which matchups you do on the way to the final. Okay? Because in a tennis tournament, obviously you have 2-person matchups. Okay. All right, now how can this happen? What's going on? Let's try to understand the phenomenon behind this. All right, he makes the point that even though each voter has a straight line preference and has a clear first, second, and third, the entire group does not have a clear first, second, and third. This is what he calls a cyclic preference. Okay, it just seems that the preference goes round and round and round. You can't tell who is the clear winner. Okay. Now let's try to represent this mathematically. Here we have a cycle, and this illustrates a case where Republican is preferred over third party, Democrat is preferred over Republican, but Democrat is not preferred over third party. I'm sorry. Democrat is preferred over Republican, but third party is not preferred over Democrat. So that's exactly this situation here. Democrats preferred over Republican corresponds to this greater than. Republicans preferred over third party, that corresponds to this less than. And here you can say that this voter represents 1 vote against third party over Democrat. All right, now, this is a way to represent this person's preference. If we have a bunch of voters, all we have to do is simply sum their preferences. So each voter is represented by a cycle like this. And to get the total preference of the group, you just add the cycles. It's clear how you add the cycles. You'll just add the corresponding numbers on the corresponding arrows and get the result. So, for instance, you could represent this previous election here. This is 5 times the first preference here. That corresponds to 5 times this cycle. So just add up the cycles with scalar multiples, and you'll get the result of the election. You'll get the preference result of the election. Okay. This looks very much like vectors, and in fact, it can be represented as vectors. We can use this vector here to represent that 7 voters prefer Democrat. I don't remember how it works here. You did 7, 1, 5. 7 voters prefer third to Democrat. 1 voter prefers Republican to third. 5 voters prefer Democrat to Republican. So you represent that as 7, 1, 5. Okay. Now let's define a vector, 1, 1, 1. Okay. Clearly, a single person cannot have this voting vector. That's not a rational choice. However, when you sum multiple voters together, you may get a component along this direction. Okay, so we're going to define this vector, 1, 1, 1. And then we're going to define a subspace that consists of all vectors perpendicular to 1, 1, 1. Now, if they're perpendicular to 1, 1, 1, they're also perpendicular to k, k, k. Okay? I can find a basis of this vector space consisting of vectors perpendicular to 1, 1, 1. This is the homogeneous condition that expresses perpendicularity. And we know how to find the basis of a solution of a homogeneous system. Here's one particular choice. It's not the only choice, but here's one particular choice for a basis. So we have, in sum, this basis. Here's 1, 1, 1. Here's the basis of the perpendicular space. So this is a basis for all possible voting vectors. Okay. Now, we have all of these preference voting vectors. Let me just go directly to the table. These 6 possibilities here, 1, 2, 3, 4, 5, 6, represent the possible preferences for an individual voter. Now we can decompose this into the basis that we have just defined. There's going to be part along the 1, 1, 1 vector and part along the other 2 vectors. Now in this diagram, he's just broken it up into the cyclic part, which is the part along the 1, 1, 1 vector, and the non-cyclic part, which is what's left over. And you can verify that this, they all have this one vector 1, 1, 1. This represents 1/3 times 1, 1, 1. This one represents minus 1/3 times 1, 1, 1. Okay. Now, clearly when you add up different voters, you're adding up vectors like this, and you're going to add up these cyclic tendencies and anti-cyclic tendencies. So if the cyclic tendency wins out by enough, you're going to get one of these voting paradoxes where you have a voter circle. All right, so let's see. Here he says that if we conduct the election as just described, then after the cancellation of as many opposite pairs of voters as possible, there will remain 3 sets of preference lists. One from the first row, one from the second row, and one from the third row. We will finish by proving that a voting paradox can happen only if the spin of these 3 sets are in the same direction. That is, for a voting paradox to occur, the 3 remaining sets must all come from either the left of the table or they must all come from the right. What he means is this. If you have an election, you'll have a certain number of people with this first preference ranking, certain number with the second, certain number with the third, certain number with the fourth, fifth, and sixth. To add up the results, what you do is you add up the results of this minus this. You can see that these 2 vectors actually cancel each other. Okay? So I might as well add these 2 together first, and the ones that disagree will cancel out. So I'll say the net is going to be A. The net result of the sum of voters with these preferences and these preferences is going to give me A times this cycle here. Okay. Same thing here. I'll have a certain number of voters with this preference, certain number with this preference. If I take the net, I'll have B times this cycle here. Now, B could be negative if there are more voters of this type than that type. But as long as I allow the possibility of A and B being negative or positive, this covers all of the cases. Similarly, I can take the net voters here, C. Okay, so I've reduced from 6 cases to 3. I only need to consider 3 cases, and I have A, B, and C, where A, B, and C can be positive or negative. And the idea is that you can only have a voter paradox if A, B, and C are all the same sign. They're all positive or they're all negative. Okay? So, frankly, I found this proof a little hard to follow. I could follow it, but it was hard for me to explain. So I'm going to give a different version that's very closely related. So let me recap here what we're trying to show. We have the results for each of the three types of cycles. We have A times the first plus B times the second plus C times the third. As I mentioned, any election can be decomposed this way. And if you take the algebraic sum of these, you simply get this result here, right? Here is minus A, here's B, here's C. So on this vector here, I have minus A plus B plus C. And the same for the other entries here and here. Now we want to show that a voting paradox occurs only if, notice the only if, A, B, and C are all negative, or A, B, and C are all positive. All right? Now, when does a voting paradox occur? Voting paradox occurs when this, and this are all the same sign. They're either all positive or all negative. So let's break this into cases. Okay. Case 1 says at least one of A, B, and C is equal to 0. Okay. So obviously the other case will be that all the A, B, and C are non-zero. But let's see what happens when at least one of these is 0. Here I use this expression WOLOG. That means without loss of generality. I'm choosing, for example, C equals 0. If I choose A equals 0 and B equals 0, the argument is exactly the same. So that's why I say without loss of generality. This is a common ploy in mathematical proofs. But I think you can see that if I can prove my case for C equals 0, I can simply adapt the proof for the case A equals 0 or B equals 0. All right, so let's suppose that C equals 0. Now, in order to get a voter paradox, then C is 0, so I cross out the C here, and I cross out the C here, and I cross out the C here. What do I have left? I have minus A plus B and A minus B. Now, in order for there to be a voter paradox, these two must be the same sign. Okay. The only way for that to happen is for now I actually had a little trouble understanding this proof, so I made up my own proof, and you can see here. It's very similar, but for me it's a little more easy to understand. It's kind of the same idea. Okay, so what we want to prove is that a voting paradox occurs only if A, B, and C are all non-negative, or A and B and C are all non-positive. Notice this is a only if. It's possible that A, B, and C are all non-negative and there's no voting paradox. Or it's possible that A, B, and C are all non-positive and there's no voting paradox. However, we can say that A, B, and C are all non-negative or all non-positive is a necessary condition for a voting paradox to occur. Okay. What does voting paradox mean? Voting paradox means that all of these three numbers are either non-positive or non-negative. Okay, so in other words, the signs of these three numbers are determined by the signs of A, B, and C. And if all of A, B, and C are not the same sign, then these numbers will not all be the same sign. Okay, so I'm going to break the proof up into two cases. Case 1, at least one of these three numbers A, B, and C is equal to 0. Now, if at least one is non-zero, let me just pick one. I'm going to say, without loss of generality, I'll say that C is 0. Now, I could use the same argument with A is 0 or B is 0. I'm just choosing C as an example. If you wanted to write it out for A and B, it would be the same proof, just twiddling around the letters. Now, suppose C is 0. Then in order for a voting paradox to occur, what must be true? Well, if C is 0, I can cross out the C here, I can cross out the C here, and I can cross out the C here. If there's a voting paradox, this number, and this number must all have the same sign. That is, they must all be non-positive or they must all be non-negative. Okay? So that's, I'm just writing that out here. A minus B, B minus A, and B plus A must all have the same sign. Now, if A minus B and B minus A have the same sign, that means that A must be equal to B. If A is not equal to B, then one is positive, one is negative. Now, if A is equal to B, they certainly have the same sign. And C is 0, so that's both non-negative and non-positive. So all three are either non-negative or all non-positive. All right, so that's a case we can take care of pretty easily. The case where one of these, or at least one of these numbers is 0. Okay, so now we can assume that all three are non-zero. And that makes the proof a little bit more easy to get a hold of. So in this case, what you can do is simply make a table of all possibilities. For instance, it's possible that all three are positive. Okay. Now, if all three are positive, then what about the signs of these numbers here? I kind of junked it up here. Minus A plus B plus C, well, that could be positive or negative. A minus B plus C, that could be positive or negative. A plus B minus C, that could be positive or negative, depending on the relative sizes of A, B, and C. So that's why I put these 3 question marks. Fortunately, we don't need to decide this case, because all we're trying to prove is that if A, B, and C are not the same sign, then it's not possible to have a paradox. Right? So I can just leave this case as it is. Now, if you think about this situation, if all three are non-zero, there's only 2 possibilities. Either all three are the same sign, or 2 have the same sign and 1 is opposite. There's no other possibility. Okay? So again, I can use this without loss of generality argument. Without loss of generality, I can take A and B being the same sign, and also without loss of generality, I could take them both plus, and I could take C to be minus. All right? If you wanted to write out all the other cases, you'd have the very same argument, but it'd just be a little bit, but it's just a lot of writing. I could fill out this entire table, take a long time, but all the other entries of the table are going to look exactly like either these 2 rows or this row here. All right, now let's consider this case where A is positive, B is positive, and C is negative. What are the possibilities for A minus B? Well, A minus B is either non-negative or non-positive. It could be both, but I'm not really concerned about that. I just want to make sure to cover all the cases. Okay, so now I have A positive, B positive, C negative, and let's look at the case where A minus B is non-negative. Okay. Then what do we have in this case? In this case, what's the sign of this? What's the sign of this one? Well, minus A plus B, that's the same as A minus B taken a negative. A minus B is non-negative, so that means minus A plus B is non-positive. And C is also negative. So this number must be less than 0. Here, I'll make a line here to distinguish these 2 cases. Okay. So in this case where A is positive, B is positive, C is negative, and A minus B is non-negative, this number must be less than 0. What about this number? Well, A is positive, B is positive, C is negative, so minus C is positive, so this number is greater than 0. So in this case where A and B are positive and C is negative, we do not have a voter paradox. And as I said, we could use this. All right, so let me cover the other case also. The case where A and B are positive and C is negative, and A minus B is less than or equal to 0. In this case, what about the signs of these? Well, I'm going to skip this one for a moment, and I'll do this. What's the sign of A plus B minus C? Well, here, I'll just do this. This is plus, plus, and minus. Okay. What about the sign of A plus B minus C? Well, I have the same argument as before. A is positive, B is positive, C is negative, so minus C is positive, so this is positive. Now, what about the sign of this one? In this case, I have A minus B is less than or equal to 0. So here, A minus B is less than or equal to 0. C is less than 0. This is also less than 0. So I have no paradox. There's no paradox here. There's no paradox here also. Okay. So you can see that when I have two positives and one negative, I will never get a paradox. Now, as I said, there are a bunch of other cases to list, but really they're going to be exactly the same. For instance, if I had minus plus plus, like this, then in this case, really I want to consider two cases for B minus C. B minus C is either greater than or equal to 0, or B minus C is less than or equal to 0. And you could list the column, the signs here in exactly the same way. Right? For instance, if A is negative, B and C are positive, you can prove that this one is going to be greater than 0. And then let's see how this works. If this is B minus C is positive, A is negative, we don't know about that, but this case you'll have that this one is less than 0. Okay. So you'll go through and you'll find in every single case that if you don't have three signs the same, you can always find two of these signs that disagree. As long as we have two signs that disagree, we do not have a voter paradox. All right, so that's how the proof of this works. It's pretty much the same idea as we have here, it's easier for me. You might think of your own proof. Okay, so that pretty much does with voter paradox. You'll have a chance to look at some of these problems and work them out.